Hey folks, in lesson 21 we're going to talk briefly about the center of mass of multiparticle systems. We've already discussed linear momentum. Within multiparticle systems we've talked about sticky collisions. And so one feature about multiparticle systems, and with these multiple particles that have different masses or different spacing about them, is that we can calculate the center of mass of those particles. And that gives us insight into the dynamics when we operate our dynamics or do our dynamics on the center of mass. So first let's define what the center of mass is and then how we can find the location of the center of mass. The center of mass is simply if you take all the particles in a system and you add up all the masses, and if you were going to balance that on your finger, where would that location be? That's qualitatively what that is. And then quantitatively, it's that location that we're concerned about. So to locate that, we're going to add up all the particles, all the mass of all the particles, and that's the mg, which is the sum of the masses mj, and if we add those up, j is equal to 1 through the number of particles. And then the location of the center of mass is simply this vector sum of these mass-weighted particle positions. So if we've got a position vector to a particular particle, we're going to multiply that by the mass, and we're going to continue to do that for all of our particles, and then we're going to divide by the total mass. Now notice in this equation that we've defined our position vector relative to a point that's fixed within the inertial reference frame. Now, if we decided that we wanted to define our position vector as the location of each particle relative to the center of mass, so essentially saying that this part here would be r of j with respect to g, then what we get is actually a pretty important result. Because if we're going to sum up all these particles, we'll just back this up, 1 over mg, then you should see here that instead of O, this is going to be G. So R of G with respect to G is equal to 0. And this result, although it may seem somewhat trivial because of the way that we derive this result, it actually isn't at all. But it proves our point in saying that the location of the center of mass of a multiparticle system would be where you would then balance all that if you could have them all connected by massless rods, because of this term here, this mass multiplied times the position of each of the particles. And so you may recognize this if you've taken statics or from your statics course, in which when the area for center of gravity or centroids, we would talk about the first moment area. So in this case, we have something that looks like the first moment mass, which is going to be a distance away from g multiplied times the mass. So that's essentially saying that the first moment of all the masses combined together is going to be balanced and is going to be equal to 0. Now this conclusion right here, where we say the sum of the moments, or the sum of the mass times the position vector, about point G is equal to 0, shows up lots of places. We'll see this in future lessons when we start talking about rigid bodies, and we'll see this actually in a moment when we start taking the center of mass and doing things with it. So this is one that you just want to commit to memory. The center of mass of multiparticle systems, and also when rigid bodies come into play, is really kind of a wonderful, special, magical point that we'll use a lot, and then we'll be able to cancel out a lot of terms in our derivations in the future. But for right now, let's apply this to the knowledge that we've already developed earlier in the chapter, and let's see how this helps us analyze these systems. So recall from lesson 20 that we used F equals ma for an individual particle that's contained in a multiparticle system. And we defined it as the mass of the particle j multiplied times the acceleration of j relative to point O, all observed in an inertial reference frame. And then what was unique about this is that we separated our force on that particle j into two forces, which were an external force plus all of the internal forces that relate that particle j to all the rest of the particles in the system. Now to relate this to the position of the center of mass, let's take this equation for this individual particle and let's put this in terms of a position. So instead of acceleration, let's call this the second derivative, the time derivative of our position. And so we'll keep our mj, but we'll replace our acceleration with a d squared dt squared as observed in the inertial reference frame of r j with respect to o, and then the right side is all the same. All right, so we have our external forces and our internal forces. And now we'll define this position of j with respect to o as j with respect to o, and then let's use a vector triad in which we have o and then we have j, but let's also incorporate the point g. So that means we'll have r of g with respect to o and r of j with respect to o, which is what we want, and then we also have here r of j with respect to g. So we can add those up so that it's r of g with respect to o plus r of j with respect to g. And then if we insert our result into our second time derivative, then we end up with a d squared dt squared as observed in the inertial reference frame, and we'll move our mass in. So mj r of g with respect to o plus the second time derivative observed in the inertial reference frame of mj r j with respect to g, and then the right hand side is all the same. And now of course we're not only interested in a single particle, but we're interested in the entire system of particles. So let's sum up all of our particles, j equals to 1 to n. We'll do this for the entire system. And so the first thing that we'll notice here is that when we sum this up, just like last time, if we sum up all the particles, then all of the internal forces cancel with each other. And so it makes this term go to 0. And when we distribute our summation in, you can recall from your calculus classes that we've actually got a lot of flexibility in the order that we put our time derivatives, our summations, and so forth like that. So I'm going to reorder this. And all that matters is that we apply our summation to each of these terms. And so I'm going to reorder this a little bit. So in this first term, let's have a single derivative with respect to time on the outside of the entire term. And then let's distribute our summation on the inside of the term. And then that'll give us our summation from j is equal to 1 to n, and then we'll have our mass, j. And then let's put this next time derivative, because we're splitting our derivative into two things, onto our position vector. And so when we do that, we end up with a d dt with respect to I of r g with respect to o. And then for our next term, we're going to leave this the same, but then we're going to leave our time derivative the same. But then we're going to distribute our summation on the inside once again. So we get the summation of j is equal to 1 to n, and then this is mj multiplied times r j with respect to g. And then this is equal to the summation of only our external forces on the entire multiparticle system. So just really quickly, all we did is we distributed our summation to each of these three terms that are left over, because this is now 0, our fj, I, and then our order really doesn't matter. And so here we separated our ddt's, and this is just going to make our life a lot easier as we begin to break this expression down. And so the first thing you should notice is that in this second term we have the sum of this moment equation, where I say moment there because it's a position multiplied times a mass, so it's like a mass moment. And so it's our mass moment, but it's about point g. And so we just said a moment ago that whenever we we have this term here about point G, then this is equal to 0. So now we can get rid of that. And then the second thing that you'll recognize is that the time derivative of the position vector of G with respect to O is the velocity of G with respect to O as observed in the inertial reference frame. So from this we get a new equation, and that's the time derivative as observed in the inertial reference frame of, and so the sum of mj here is mg, and so it's the time derivative of mg multiplied times the velocity of g with respect to O as observed in the inertial reference frame is equal to the sum of the external forces. And so this internal part here is the linear momentum of the point G, the linear momentum of the center of mass. And so we can write that as P of G as observed in the inertial reference frame. The time derivative of this is equal to our total external force. And so, and also we can write this as mg multiplied times the acceleration of G with respect to O as observed in the inertial reference frame is equal to the sum of all the external forces. So any of these three expressions is a nice concise way to tell us about the motion of the center of mass. And we see a couple of things in that if the time derivative of linear momentum of the center of mass is conserved, then that's telling us that there are no external forces on the system, or vice versa. If there are no external forces on the system, then the time derivative of the linear momentum of the center of mass is equal to 0. In addition, we've got F equals ma right here. So the sum of the forces of all the external forces is equal to the mass of all the particles multiplied times the acceleration of the center of mass. So let's put this into practice in a problem. Here we see the same system that we used in lesson 20 to develop the equations of motion. We were talking about the individual particles. And when we developed the equations of motion of this system, we got the following. X double dot is equal to a big expression, and then we have theta double dot is equal to, and we noticed that there was a simple pendulum plus cosine theta over L multiplied times this another big expression, which is actually X double dot right here. And so we made some observations about this system, and they were that the acceleration of the mass q, which is determined by X double dot, is reliant upon the state of the pendulum itself. So it's reliant upon the other coordinate, which is theta, and then also theta dot, and then both masses. The acceleration of theta double dot, which is the angular acceleration of the pendulum, has the simple pendulum, and then it is not reliant upon the state of the other mass, but it is reliant upon the acceleration. And so if we were to take this system and say, if we just want to apply an initial condition of theta at time 0 is equal to at some angle, and then let that go, then how would we solve that? Well, initially you look at this and say it's massive. There's a lot of information here. We need to put this into our ODE 45 or an equation solver. But what we're about to see is that if we analyze this system in terms of the center of mass of the system, then we can actually gain some insight on how that system would behave with that type of position perturbation or initial position condition. So let's solve this problem. So once again, what we're doing is we want to see what happens when we release the system from rest. And let's just say x at time 0 is equal to 0, and then we've got theta at time 0 is equal to theta naught. So we apply our reference frames and coordinates as we had before. And so here's our coordinate x, here's our coordinate theta. We have an inertial reference frame. where we have the EX direction, the EY direction. We have a non-inertial reference frame that's a polar frame in which we have ER and we have E theta. And we also determined that the transformation matrix between these basis vectors is EX, EY, and then ER, E theta. And we have sine theta minus negative cosine theta, then cosine theta, and sine theta. And what we're going to do is we're going to solve for the motion of this system using the center of mass. And the center of mass between these two particles is located somewhere about, say right there. There's our center of mass. We're going to call that point G. And so first we need to determine the position vector for point G. And so that's R with respect to O is equal to 1 over mg multiplied times the summation, and this is going to be from j equals 1 to 2 because we have two particles, and that's mj of rj over rj with respect to O. And so this is where the position of mass q, rq with respect to O, is equal to x in the EX direction, and then the position of mass p, rp with respect to O, is equal to x in the EX direction plus L in the ER direction. And so to finish calculating the location of the center of mass, we get the mass of P. So we're going to weight these positions, the mass of P, RP with respect to O, plus the mass of Q multiplied times RQ with respect to O, according to our formula, and then divide that by MP plus MQ. We plug in all of our terms, and so for our position vectors, so we get MQ, x in the EX direction, so now we're putting this in our basis vectors, plus MP, and then its position, x in the EX direction, plus L in the ER direction, divided by, and then this is mg, total mass of the system. We'll collect our x terms, and we get MP plus MQ, x in the EX direction, plus MP, L in the ER direction, all divided by mg. We'll see that this term cancels out. And then finally, the location of our center of mass G is x in the EX direction, plus MP over mg multiplied times L in the ER direction. And in the book, in this example, which is similar to the book, shorten this to be, which is called this L with a tilde over top of it. So essentially, this L tilde being equal to MP over mg L. So it's a ratio of the length L. And so this is telling us that if MP is a greater mass than MQ, then it's going to be over half the distance. And then if MQ is a greater mass than MP, it's going to be less than half the distance, or half the length down that pendulum. And so now that we've located our center of mass using our basis vectors that we've set up in this system, we can now solve our dynamics of this system as normal. So we've got Rg with respect to O is equal to x in the EX direction plus L tilde in the ER direction. Our velocity as observed in the inertial reference frame is going to be x dot EX, and then we'll just call it L hat theta dot in the ER direction, and then the acceleration of G with respect to O as observed in the inertial reference frame is equal to x double dot in the EX direction plus L hat theta double dot in the E theta direction minus L hat theta dot squared in the ER direction. So all this should look pretty normal to you. And essentially, it's the equation for this system with a shortened pendulum. But here's what's different, is that when we're applying Newton's second law, we don't need to apply Newton's second law to each particle individually anymore. We can apply it to the center of gravity. And we said earlier that mg multiplied times the acceleration of the center of mass as observed in the inertial reference frame is equal to simply all the external forces on the system. So when we draw a free body diagram, we no longer need to draw two free body diagrams. We can draw one free body diagram of the entire system, which is this. And our forces that are applied to this system are going to be the force due to gravity, so it's mq multiplied times gravity, and that's in the negative EY direction. And then we have a normal force that's applied to the system in the EY direction. And then we have MP, that's gravity in the negative EY direction. And so we only have three external forces. And so when we add this up, our total external forces are equal to N minus MQ minus MP, or MQG minus MPG in the EY direction, or we can also write that as our total external forces are N minus mg multiplied times gravity in the EY direction. And hopefully you can see that this altogether is a much simpler system to solve than what we did before when we got the full equations of motion. So let's see what happens when we put these together. We're going to insert this into the mg ag with respect to O as observed in the inertial reference frame is equal to all the external forces on the system. And when we do that, we get mg multiplied times x double dot, this is in the EX direction, plus L theta double dot in the E theta direction, minus L theta dot squared in the ER direction, and then this is equal to, these are L hats, this is equal to N minus the mass of the center of gravity multiplied times gravity is equal to EY, or multiplied times EY. It's in the EY direction. Also notice I'm saying center of gravity sometimes. Center of mass and center of gravity are the same thing in this system. Now something to notice here is that in this equation that we have here, that we've set this up so many times before, because we've looked at this as an entire system, we actually have two scalar equations in the single vector equation, but we have too many unknowns because we don't know x double dot, we don't know theta double dot, and we don't know our normal force. So we can't solve this system without measuring the normal force and know what's happening in the system itself. And to do so, we'd have to break that apart into our larger equations of motion. However, what's nice about this approach, considering the center of gravity, or the center of mass, is that we can still gain insight in how this system behaves. And the reason why is because this is equal to d dt as observed in the inertial reference frame of our linear momentum of g with respect to O as observed in the inertial reference frame. And this is equal to N minus mg times gravity in the EY direction. And so you can see here that because there are no forces in the EX direction, so this is plus 0 in the EX direction, the time derivative of our linear momentum of the center of mass is equal to 0, so linear momentum is conserved in the horizontal direction. And so recall that what we're doing here is we said that we want to gain insight in this system in which we pull our pendulum back a certain angle theta naught and then let it go. Our initial velocity of the center of gravity, which is what we just did our analysis on, is 0 and it's going to maintain 0 because linear momentum is conserved in the EX direction. Then it's going to maintain a 0 velocity, so EX dotted with VG with respect to O in the inertial reference frame is going to be 0 for the entire time that this system moves. And so when we pull the pendulum back and we let it go, then mass Q is going to move to the right. It's going to come to a stopping point, and when it does that, the pendulum is going to be in the exact opposite position, and the center of gravity is going to be in the same place. G, this point, is never going to move back and forth, so somewhere in the middle, or directly in the middle, our pendulum is going to swing. It's going to be straight down, and then G is going to be lower, and so we see that the center of gravity simply moves up and down and up and down as mass P oscillates back and forth, and then mass Q oscillates back and forth, and then P oscillates back and forth as well. And so the system itself oscillates back and forth around the location of the center of gravity. So let's write the linear momentum about the center of gravity out and analyze that. And so we get this expression, P of G with respect to O, as observed in the inertial reference frame, is equal to the mass, the whole center of mass, multiplied times x dot in the EX direction, plus L hat in the theta dot in the E theta direction. And then we know that E theta is equal to cosine theta EX plus sine theta EY. And so our entire expression is mg times x dot plus L hat theta dot cosine theta in the EX direction plus mg L hat theta dot sine theta in the EY direction. And so if momentum is conserved in the EX direction, and we're starting out with an initial velocity of 0 and maintaining that that's 0, then we have this conservation equation now that tells us that this term, well, mg x dot plus L hat theta dot cosine theta EX is equal to 0. And so for that to be true, this term must be 0. So we get that x dot plus L hat theta dot cosine theta is equal to 0. And if we integrate this expression, then we get a nice simple expression where x is equal to negative L sine theta, or L hat sine theta, plus our initial position x naught, x at time 0. And this tells us something really important. It tells us that the center of mass, it tells us that the location of mass Q is equal to this very simple expression. So it's minus L hat sine theta plus our initial position of this system. And so in this situation where we're taking our system, we're simply pulling the pendulum back and then we're just letting it go with this initial criteria, we've gained incredible insight into how mass Q moves, and then as a result, related to mass P, how it moves, because we've determined this expression. And so without having to go through all the rigmarole of deriving equations of motion, figuring out how to solve these, in fact we did this completely analytically, and by basing this around the center of mass of the system, and then looking at how the time derivative of the linear momentum of that center of mass is equivalent to all the external forces of the system. Alright, that does it for lesson 21, and I'll see you in class.